Hello. In this section, we are going to continue talking about logarithms, but we are going to introduce some specific properties of logarithms. All of these properties are based off of properties of exponents. Because a logarithm is defined as an exponent, then the properties of exponents can be applied to logarithms. So the three properties that we are going to look at are called the product property, the quotient property, and the power property. The product property says that if you have the logarithm of a product, such as the logarithm with some base b of the product x times y, this can be written as the sum of two individual logarithms, specifically the log base b of x plus the log base b of y. The quotient property can be, it states that if you have the logarithm of a quotient, such as the logarithm of x divided by y, we can write this as the logarithm of x minus the logarithm of y. And then the power property states that the logarithm of some value raised to a power or raised to an exponent, such as x raised to the power of p. We can write that in a different form where the p gets multiplied by the logarithm, right? So the logarithm of x raised to the power of p is equal to p times the logarithm of x. Now, like I said, all of these properties are based off of corresponding properties of exponents. For example, and what I'll do is I'm going to walk through the proof of the product property. The proof of the other ones can be left as exercises for you. They're not really difficult. I'll walk through the first one, though. And just to point out the corresponding properties of exponents that these are based off of. So the product property is based off of this property. If you have something like b raised to the power of m times b raised to the power of n, this is equal to b raised to the power of m plus n, basically. Okay. The quotient property is based off of the property of exponents that says something like b raised to the power of m divided by b raised to the power of n is equal to b raised to the power of m minus n. So if you divide two exponentials with the same base, you can write it as a single exponential and you just subtract the exponents. And then the power property, the corresponding property of exponents that this is based off of is this one. If you have something like b raised to the power of m raised to the power of n, a power raised to a power, this can be written in a different form where you just multiply the exponents together. Okay. So just to illustrate the connection, at least for the product property, let me walk through the proof. And do that right down here. So if I were to say let m equal log base b of x, okay, define that way. And if I were to write this in exponential form, that would imply that b raised to the power of m is equal to x. Okay. Then if I define another term, which I will call n is defined as log base b of y. In exponential form, this can be written as b raised to the power of n is equal to y. Okay? So what that means is that the product of x and y is equal to b raised to the power of m times b raised to the power of n, right? And that, according to the power, this property of exponents that we stated here, right? This is equal to b raised to the power of m plus n, okay? So in other words, just removing the middle piece here, right? What I have is that x times y is equal to b raised to the power of m plus n, okay? So what happens if I take this expression and write that in logarithmic form? Well, what I would get is log base b of x, y is equal to m plus n. And then how are m and n defined? Well, I defined them over here, right? So if I plug those in, I get log base b of xy. M is equal to log base b of x. N is equal to log base b of y. And that is the product property of logarithms, right? So that's the mathematical proof, right? Again, based off of this corresponding property of exponents. You could walk through a similar proof for the other properties using the corresponding properties of exponents. It's not difficult. You just kind of follow the same kind of pattern that I did here. But what I want to do for now is I want to go over some examples where we apply these properties. So what I'm going to do is I'm going to use the product property of logarithms to write these expressions as sums. Okay. So this first one, let me get my notes here, right? Log 2xy, that could be written as log 2 plus log x plus log y. So the product property can be extended to the product of however many things are being multiplied together, right? In this case, I've got 3 quantities being multiplied together, so the resulting sum will involve 3 logarithms. Or here, log base 2 of 2xy, this is equal to log base 2 of 2 plus log base 2 of x plus log base 2 of y. And then it's always good to see if you can simplify anything anymore. Log base 2 of 2 is just equal to 1. That's from one of the properties of logarithms that we covered in the previous section, right? So the other 2 expressions don't simplify down anymore. But the final result can be written as that. Okay. Let's do a couple of examples where we apply the quotient property. And we are going to write the logarithms as a difference, right? So this is just equal to log base 7 of z minus log base 7 of 49, right? And then we should look to see if we can simplify anything down. This one, log base 7 of 49, we would say 7 raised to what power equals 49? That power would be 2, right? Because 7 squared is equal to 49. So that means this logarithm is just 2. So I can rewrite that as 2. And then over here we have log base 7 of a minus log base 7 of 14, right? And that cannot be simplified any farther. Power property, let's look at a couple of examples here. The natural logarithm of x to the fifth, I can write that as 5 times ln x. The natural logarithm of e to the fifth, I could write that as 5 times ln e. And ln of e is just 1, again, because it's the base e logarithm of e. And that was from a property we covered in the previous section. So this one just simplifies down to this, right? This one, the logarithm of the cube root of x squared, I could write this as log, instead of using the root terminology, I can write it in exponential form. So cube root is the same thing as raised to the power of 1/3, but then, so we have basically x squared, right, raised to the power of 1/3 is what we have. And this is equal to log, you multiply the exponents, right? So x to the 2/3. And then the 2/3, the exponent can be written as the product of 2/3 times log x. So that would be the equivalent form. And then you can also apply more than one property to a single expression, right? So let's say that I want to write an expression in expanded form as the sum or difference of logarithms. Let's do a few examples where we look at that. With this first one here, log base 7 of AC divided by 5D. I could start by applying the quotient property and write this as log base 7 of A times C minus log base 7 of 5D. And then I can apply the product property to each of those. So this is equal to log base 7 of A plus log base 7 of C minus log base 7 of 5 plus log base 7 of D. And then, without the parentheses, I could just write this as log base 7 of A plus log base 7 of C minus log base 7 of 5 minus log base 7 of D. Okay. Down here, I could start by applying the product property. I could write this as ln of x squared plus ln of y. And then I could apply the power property to this first one and write this as 2 times ln x plus ln y. And then we'll just do one more along these lines. With this one, I've got log base 2 of the square root of 4x over yz cubed. I could start by writing this, instead of using the root, use the exponential terminology. So I could write this as 4x over yz cubed raised to the power of 1/2, right? Raising something to the power of 1/2 is the same thing as taking the square root. Then I can apply the power property and bring the exponent out front. This is equal to 1/2 times log base 2 of 4x over yz z cubed. And then I can apply the quotient property. This is 1/2 times log base 2 of 4x minus log base 2 of yz cubed. Okay. And then I can apply the product property to each of those terms. So this is equal to 1/2 times log base 2 of 4 plus log base 2 of x minus quantity log base 2 of y plus log base 2 of z cubed. And let's go ahead and write that without the parentheses. This is equal to 1/2 times the quantity log base 2 of 4 plus log base 2 of x minus log base 2 of y minus log base 2 of z cubed. Okay. Okay. And then let's see what we can do here. Okay, so well, log base 2 of 4 can be simplified, right? Because 2 raised to the power of 2 is equal to 4. So log base 2 of 4 is equal to 2. Okay. That one stays the same, minus log 2 of y. And then for this last one, I can apply the power property, and the 3 gets moved out front, right? So this is minus 3 times log base 2 of z. And then finally, I can distribute the 1/2 as my final step here. So 1/2 times 2 is 1. 1/2 times log base 2 of x is just that. 1/2 times log 2x. Okay. 1/2 times log 2y, the next one. And then 1/2 times 3 log 2z. So that's minus 3 halves log 2z. Okay. So there's the expression in its fully expanded form, right? So there's the original expression. Down here, this is an equivalent way of writing the same thing, applying the properties of logarithms. These properties can also be used in the reverse. If you start with something that's a sum or difference of logarithms, you can then consolidate them into a single logarithm. Okay, so let's do a couple of examples like that. Oopsie, sorry about that. Okay, so for this one, we have the difference of two logarithms. So I can write that as a single logarithm by applying the quotient rule, right? This would be equivalent to the logarithm of 4x minus 3 divided by x. Or this one, I can start by up here applying the power rule. So this is equal to log base 2 of z plus log base 2 of y to the 4th. And then I can apply the power property and write this as log base 2 of the product z times y to the fourth. And let's try that for this one as well. This one, I could start by applying the power property to the first expression. So I've got ln of x cubed plus ln of x minus 2 minus ln of 5. And then I can use the product rule of logarithms to combine the first two terms together. So that would be equal to ln of x cubed times x minus 2 minus ln 5. And then I can use the quotient rule of logarithms to combine these last two terms together. So that would be ln of x cubed times x minus 2 divided by 5. Okay, like so. So there's a few examples of how to apply these rules to either expand an expression into a sum and difference of different logarithms, or to consolidate an expression into a single logarithm. Let's look at a couple of other examples now where we are told, in this case, that log base b of 2 is approximately equal to 0.4307. Log base b of 3 is approximately equal to 0.6826. And log base b of 7 is approximately equal to 1.2091. And I want to use these to estimate these values. We'll start with log base b of 21. Okay? So what I can do is because 21 is equal to 7 times 3, I can rewrite this as log, say that this is equal to log base b of the product of 7 and 3, 7 times 3, right? And then I can use the product rule and write this as log base b of 7 plus log base b of 3. And then up here, we're told that log base b of 7 is approximately 1.2091. Right? 1.2091. Log base b of 3 is approximately 0.6826. And if you add those together, you get 1.8917. Similar approach here. Log base b of 9, well, 9 is equal to 3 squared, right? So I could write this as log base b of 3 squared. Then I could apply the power rule and write this as 2 times log base b of 3. And this is approximately equal. Log base b of 3 is approximately 0.6826, so this is about 2 times 0.6826, or it's about 1.3652. All right. Now, we're going to wrap up this section by going over a very important theorem. This is called the change of base theorem. What it does is it allows us to take a logarithm in one base and rewrite it in the context of another base. And this is really handy for, let's say I have a logarithmic expression, something like log base 5, what do I got here, of 20 equals x, okay? And you want to figure out what x is, right? It's not obvious from this expression, right? Because it would be basically saying 5 raised to what power equals 20, right? It's going to be some number between 1 and 2, because 5 raised to the power of 1 is 5. 5 raised to the power of 2 is 25, right? But we don't know exactly what that is, and it's not obvious. Furthermore, most calculators wouldn't necessarily have the ability to do this, because a scientific calculator would have a common logarithm button or a natural logarithm button, right? Base 10 or base e, but not necessarily a way to evaluate a base 5 logarithm. So now that we have some additional tools, some other properties of logarithms, we can actually find a way to evaluate this. The way we could do that, we could start by rewriting this in exponential form, right? So it would be 5 raised to the power of x equals 20, okay? And then we could choose a logarithm of a different base, of any base we choose, but it makes sense to choose either base 10 or base e, because our calculators are equipped to do those types of logarithms. And I take the logarithm of both sides. Let's say we choose natural logarithm. Then it would be ln of 5x, 5 raised to the power of x, equals ln of 20. Then I could apply the power rule of logarithms, and this first one I could bring the exponent out front, right, and write it as x times ln 5 equals ln 20. And now I can solve for x by dividing both sides by ln 5, right? So x is equal to ln 20 divided by ln 5, right? So by applying the power property of logarithms, I was able to take this expression and write it in terms of just natural logarithms. And this is something that I could easily just plug into my calculator. I can evaluate ln 20 divided by ln 5 on my calculator because it has a key for natural logarithms. Okay. Basically what I did here is it's a proof of what we call the base change theorem, which is stated right here. If we let a and b be positive real numbers, such that a is not equal to 1 and b is not equal to 1, then for any positive real number x, log base b of x can be written as log base a of x divided by log base a of b. Okay, so I can take any logarithm and I can rewrite it in terms of a logarithm of a different base, right? For the new base, I take the logarithm of the argument of the original logarithm, and I divide that by the logarithm of the base of the original logarithm. Okay. Now you can choose any value you want for a, but there's only really two values that make sense, either e or 10, so that we can use either natural logarithms or common logarithms, right? So, for example, log base b of x can be written as log x divided by log b, or ln x divided by ln b. So this is a really useful formula because it then gives us the ability to use a scientific calculator to approximate the value of any logarithm, because I can rewrite it in terms of common or natural logarithms. Let's go over a couple of examples. Right? Evaluate log base 7 of 15. So that would be the exponent that you raise 7 to in order to get 15, right? We know 7 raised to the power of 1 is 7. 7 squared is 49. So this logarithm will be some number between 1 and 2, but by inspection, we don't know exactly what that value is. But using the base change formula, and then choosing either natural or common logarithms. I can write this as, I'll choose natural, that's usually my preference, but ln 15 divided by ln 7. Plug that straight into your calculator, and you'd get approximately 1.3917 if you did that. Okay? Or similarly, log base 5 of 0.3. Using the base change formula, this could be written as, say, ln of 0.3 divided by ln 5. And evaluating on that on your calculator, you get about negative 0.7481. That wraps it up for this section. Thank you for watching.